Welcome to this video on the geometry of factoring. We will explore how to visualize polynomial areas using physical algebra tiles. Algebra is often taught through abstract rules. However, quadratic factoring is fundamentally a study of spatial dimensions. By using physical tiles, we transform trinomials into tangible structures, bridging the gap between symbolic logic and geometric intuition. This method has deep roots. Long before modern notation, mathematicians like al-Khwarizmi used geometrical demonstrations to solve equations, literally completing the square by drawing in the sand. This reminds us that algebraic solutions are more than just numbers, they represent physical truths. In Part 1, we will examine the anatomy of algebra tiles. The first building block is the unit tile. It is a small square with side lengths of 1 unit. Its area represents the constant term in a polynomial. Next is the variable tile. This is a rectangle with one side of length 1 and the other of unknown length x. It represents linear terms in an expression. Finally, we have the quadratic tile, the foundation of our work. This is a large square with side lengths of x, representing the quadratic term. Together, these create a visual hierarchy. Units represent constants, variable tiles represent linear terms, and the large square represents the quadratic term. Part 2 explores how we use area as a universal language for these expressions. The fundamental equation here is area equals length times width. In algebra tile modeling, the polynomial represents the total area of a structure, while the factors represent its dimensions. For example, a binomial length like x plus 3 is modeled by placing one x tile and 3 unit tiles end to end. This creates a single dimension used to construct a full area. When we expand a product like x plus 1, x plus 2, we are forming a rectangle. The resulting area is filled by 1x squared tile, 3x tiles, and 2 unit tiles. This mapping guide summarizes the relationships. Constants, linear extensions, and quadratic foundations all correspond to specific geometric shapes. In Part 3, we will look at the core logic of the factoring process. The rule is simple. Every tile in the expression must fit into a single, perfect rectangle. If you cannot form a rectangle without gaps or overlaps, your configuration is incorrect. Beyond just building rectangles, algebra tiles offer unique cognitive advantages. They help us develop spatial reasoning, enhance tactile memory through physical interaction, and turn complex math into a rewarding puzzle-solving task. Moving to Part 4, let's look at the practical application of this method, step by step. Our goal is to factor the expression x squared plus 5x plus 6. We must arrange one large square, 5 rectangular tiles, and 6 unit tiles into a single, complete rectangle. The first step is simply gathering our inventory. We need exactly 1 x squared tile, 5 x tiles, and 6 unit tiles. Next, we arrange them. Place the x squared tile in the top left corner. Split the 5x tiles by placing 2 on the side and 3 on the top. The 6 unit tiles will then perfectly fill the remaining void to form a 2x3 grid. Once the rectangle is complete, look at the side lengths. You will see the dimensions of your rectangle correspond to your factors. You have successfully mapped the symbolic expression back to its geometric parents. In Part 5, we address the challenge of negative values. In most tile sets, the red side represents negative values. These tiles represent subtracted area or inverse dimensions, which requires us to use a new logic, the zero pair. A zero pair consists of one positive tile and one negative tile of the same type. These pairs allow us to add or remove area without changing the total value of the polynomial. To factor an expression like x squared minus x minus 6, we use these zero pairs strategically. By adding and subtracting the right number of tiles, we can force the pieces into a perfect rectangle. Finally, Part 6 looks at more advanced geometric structures. When the leading coefficient is greater than 1, we start with multiple large squares. The tiles must still form a single rectangle, often resulting in longer, thinner configurations. Even for complex expressions, the spatial logic remains consistent. You are solving a jigsaw puzzle where the pieces are strictly defined by the equation, proving that algebraic factoring has a physical counterpart. As Sophie Germain once said, algebra is but written geometry, and geometry is but figured algebra. This visual method honors that deep connection. Thank you for watching this video. We hope this exploration helps bridge the gap between symbols and shapes. If you have questions or want to learn more, feel free to reach out via the contact information on your screen. This video features content and inspiration sourced from a variety of educational materials. For a full list of these image references, please see the slide displayed on your screen. We would like to acknowledge the additional resources and references that contributed to this video. Thank you for joining us in exploring the geometry of factoring.